So I've got a copper pipe here and a capacitor which just happens to fill in the pipe, and what we're going to do is going to drop that, ready when you are, Patrick, and fairly obviously accelerates at around about 9.81, although obviously there's a little bit of friction. Do you want to just do that again so they can check it out? Okay, pretty quick. And what we're going to do now is drop in a magnet instead. Okay, just so it doesn't stick to the side, can you? So it's not a magnetic material, it is copper, it's not going to be able to be magnetized. Go for it. And obviously by now you'd expect it to have dropped out the bottom, but it's not. There we go. Okay, so around about what, 5 seconds? Let's just try that. So 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7. There we go. 7 seconds to drop around about a meter. So why is it doing it? It's Lenz's law, and that's because of the induction braking that you're getting. Okay, just want to show you the effect of inducing magnetism. So one of the effects of Lenz's law. Here I've got a pendulum with some very strong magnets on the bottom. And what I can do is just get that moving. And if I take an aluminium sheet, okay, so this is not magnetic, and I put it underneath, then I can get that to stop almost immediately. Okay, so if I slide it underneath, you get a massive amount of braking. Okay, so I can show that if I move it away, then actually that creates a force on it as well. So this is just an aluminium sheet, as I say. Look, it doesn't stick to it, okay, not like that does. So it's not attracting to it. What it's doing is it's creating an electromagnetic force in here, sorry, an electromagnetic field in here, which then opposes this one. Okay, so as I move it across, oops, and gently move it across, as it moves, it creates a current in here that flows around, and that's what stops it moving. This is what you call induction braking, just like you have on fairground rise. Nothing to wear out, but it stops the movement very quickly. Okay, here's another example of induction braking. So here I have a pendulum, okay, and I've also got a horseshoe magnet. So if I just put that horseshoe magnet in the middle, you can see it's aluminium because it's not sticking to the plates at all. And I've got a brass upright, so that won't affect it either. That's not magnetic. So if I swing that through, then it's a fairly strong magnet, so it will slow it fairly quickly. Okay. And again, it's because as these move relative to each other, the magnetic field, the permanent magnets here, will induce current which flows around and around inside our plate here. Now what I'm going to do is swap it to one where the current can't flow around. Okay, so again, just have a look at that. Okay, so that's about 8 swings. If I take that away, you know, there's plenty of swings. Let's swap it. Here we are with exactly the same pendulum, but this time we've laminated the core. We basically got it made of layers. We have a complete shape, but the current can't flow round and round. And if you notice, it's not having any effect on the swing. So the magnetism is not induction braking because it can't induce a current into this. It can still induce an EMF, but because there's nowhere for it to flow, there's not a complete circuit, you don't induce a current. If it's solid, then inducing an EMF across the plate will cause current to flow in it and therefore creates a magnetic field to fight against the magnetic field here. So induction braking, magnets fighting magnets.